Okay, let's now discuss the difference between internal circuits and USB universal serial bus. Now, the internal circuits are a very good example of representing how parallel data transmission is combined with synchronous data transmission. So all components within your computer operate on the principle that transmission is carried out on these tiny, short parallel channels. Why? Because all internal transmission needs requires immense speed to keep up with the CPU's processing rate. So that means that, and there is no doubt that sending multiple bits over multiple channels has the ultimate speed provision. So, and again, since the distance of these cables is very short, there is less chance of data skewing. Data skewing operates in the chance of data skewing, which is a very prominent problem in a parallel data transmission, only increases with the length of the cables. But now, since we're using only very tiny, small cables, that is not an issue for the internal circuitry. We're having the immense speed of data transmission, parallel data transmission, and since the cables are short, we are not worried about data skewing. In this case, this internal circuits are primarily operating on parallel synchronous data transmission. Now, what is synchronous data transmission? Synchronous, if you remember that um, your data is basically communication between the different devices are controlled by an internal clock. Data is synchronized. There is a time aspect between all different pieces of data. Now, as you can see here, that all internal components of your what you call it computer are synchronized. All activities inside your computer are synchronized, and they are controlled by some sort of clock mechanism, which we are familiar with as the internal clock. So the processor clock maintains all activities inside the computer. Because of this, those are known as synchronized data transmission. Now, we can understand synchronized data transmission, the effect of synchronized data transmission, specifically if you talk about terms like concepts such as pipelining. Now, pipelining means that we have multiple components within the processor that are performing different tasks on different instructions at different clock cycles. But these activities operate in such a synchronized manner that every time a clock cycle increases, one activity shifts to another stage and another activity enters the pipeline. So this is a very synchronized activity. For example, this diagram can be used to represent the effect of pipelining. Pipelining is not yet part of your syllabus, but this is just for giving you an idea of what synchronized activities look like. As you can see here, my process, uh, travels between different process states. We can say that this IF means instruction fetching, instruction decoding, operand fetching, instruction execution, and result write back. Now, these are different stages that an instruction has to be carried out, that instruction passes through before it is considered complete. Now, we will be studying this later in the von Neumann architecture, what these stages mean individually. But right now, for the sake of understanding, just imagine that these are different stages, that different tasks that are performed by different components on in a single instruction before it can be considered complete. We do understand a processor is basically a sequential machine, and what it does is basically it executes instruction in sequence. Now, the execution of instructions requires these individual stages to take place, and these individual stages are handled by individual parts of my processor. We will call those as processing units. Now imagine that in the first clock cycle, my first instruction, this 1.1 means my first instruction has entered my first stage. 1.1 first instruction enters first stage. Now this first instruction will move to the second stage in the second clock cycle. Meanwhile, my first component is now free because my instruction has passed through it to the second component, this one. In which case, since my first component is free, we are allowed to enter a new instruction in its first stage. And this is why this is actually the effect of pipelining. You will see that in the third clock cycle, my first instruction has entered my third phase. My second phase is now free to add the second instruction. Now second instruction enters the second phase, and the first unit is again free, because of which I introduce a new instruction 3.1, third instruction, the first phase, third instruction, first phase in my pipeline. And you notice that each time my clock cycle increases, my components start introducing new instructions in my pipelining. So right now, my first instruction enters my fourth phase, second enters my third phase, third instruction enters my second phase, and my we have a new instruction entered in my pipeline. And finally, in my fifth clock cycle, we have introduced my first instruction enters its final stage, second moves on to the fourth stage, third moves on to the third stage, and the fourth instruction moves on to the second stage, and the fifth instruction enters my pipeline as a new instruction. As you can see here, this effect, ultimately, this pipelining causes the saving of CPU clock cycles, and you're capable of executing more instructions requiring less clock cycles. This, again, I repeat, this is not part of your syllabus, but I just want to show you an example of what synchronized activities look like. And as you can see here, after each clock cycles, and this is my timing mechanism, each clock cycle, my processor is progressing from one state to another, and data is shifting between these components based on this timing signal, which based on this clock mechanism. So this is a very good example of how synchronized activities take place. So as our as considered our example, our buses, the internal channels, since they're parallel. So our parallel channels, as mentioned before, parallel bits are capable of sending multiple bits over multiple channels. So internal buses can be 8 bits, 16 bits, 32 bits, or 64 bits. 64-bit bus, as we will later see an example of a 64-bit bus, is our address bus or our data bus. Now, this bus means that I'm capable of sending 64 bits at the same time over this channel. And since the activities are synchronized, that means my internal circuits rely on parallel synchronous data transmission. Now, coming to my example of asynchronous data transmission using serial channels. The most common example that comes to mind is the universal serial bus. Now, universal serial bus is a very common device that we use in our computers. All computers come equipped with different variants of USB. You have type A, type C, type A 3.0, so on and so forth. And it is a very common port that we use for to connect all external peripheral devices. It could be the flash disk, it could be the mouse, keyboard, and right now we can connect chargers as well. So all of these ports are basically connected on some variation of the universal serial bus. But what is the universal serial bus? As the term suggests, it is a channel bus. Buses are only channels, and it is supporting serial data transmission, that is one bit over time or a single data transmission. And the term universal implies that all computers should support, are capable of supporting some variant of this universal serial bus transmission. And it is that because of this, universal serial bus has boomed. It has become the standard of peripheral device connectivity in all computers, all smartphones. And it is this reason that it is very easily maintainable, easily replaceable, because it's a very common thing. But basically, what we need to understand is a USB cable is typically divided into four separate sub cables. We have four sub cables. We have two for data. You can see here that this represent diagram basically represents that. We have white and green, two for data, one red for power, and then we have a black cable for ground to avoid any sort of short circuiting. Now, why do we have power cable as well? Because you are aware that modern USB cables and ports are capable of charging as well. So if you want to charge your device, the power section of this USB cable should be able to do that. And we have two separate data transmission channels. Now, they are serial. We just understood that one data transmission line for transmitting one bit at a time. Then why do we have two transmission lines here? That's okay. That's fine. That doesn't mean that I'm not carrying out serial data transmission. Now imagine that I have two pieces of data. I'm going to call this data one, and I'm going to call this data two. And I have two separate data transmission lines like we do here. Now, what that means is that I'm capable of sending the different bits of these two individual data pieces, one bit at a time on this separate channel. So basically what that means is that if I'm making use of these both transmission channels to send device to, for example, my computer, right? Now, if I'm sending using these both simultaneous channels to send these two data, that means that all of the bits that are being transferred here on this channel are linked to data one, and all of the bits being transferred here on this channel are linked to data 2. And that means that both bits, even though these channels will be very close to each other, these both channels are transferring data which is not related to each other. This data 1 can be MP3 file, this data 2 can be a PDF file, and they're both being transferred in the same direction. And data, and that's okay. You can, in fact, you can have multiple channels connected together like this, all serial channels, each channel transferring different data items simultaneously on different channels. So because of this, even if these bits do arrive out of order, it doesn't make any difference because this is not considered as skewing. Skewing happens when the data transmission lines are transmitting the same data. Now, if you remember that skewing occurs when I am sending multiple bits over multiple transmission, 1, 2, 3, 4, 5, 6, 7, and 8. Now imagine that I'm trying to send this data in exactly this order over this channel. So imagine that if I send this data, this bit on this channel, 0, 0, and 1, and 0, and 1, and 1, 0, 0, 1, 0, 1, and 0. One more bit. Okay. Now imagine that I have these independent channels sending data, this one single byte, this entire byte simultaneously from my sender to receiver on this parallel channel. Now imagine that I am sending this one complete data simultaneously on this stereo transmission. And what skewing means that these bits arrive on the destination out of order. Why? Because the individual channels may have a slightly different data transmission rate. Because of this, bits may become out of order. Now imagine that because of that, my bits turn out to be something like this. Now, even though it's still ones and zeros, but what happened is that this bit got to my destination. This bit got to my destination before this. Because of this, my data shifted here. Similarly, this bit got before this one. Because of this, my data transmission shifted over here. And this results in a completely different value. And this is skewing. Now, skewing only occurred that bits, both bits are traveling simultaneously. They can arrive out of order. This one can arrive before, this can arrive after, because these individual channels may have different transmission rates as well, but that won't make a difference because they're not related to each other. Despite being because this is a single channel, even though they're transferring at different rates, at different speeds, they will still remain in order, because first this will be reachable here, then this, then this, then this, then this. It is possible that this entire byte will arrive before this byte, but the byte is still intact. Over here, the bits become out of order. So that's why this is a problem in skewing. But in parallel data transmission, you can add serial data transmission, you can have multiple channels, because they will be all sending, each channel will be sending data separately, serially. This is what SATA port is. SATA is actually supporting many channels, and all channels are sending different pieces of data in serial manner, allowing for faster data transfer. So this is the difference between my USB versus serial. Now, again, why is USB considered a very, in demand, or why is considered very, what you call it, popular, is because one very important feature of USB, apart from this basic combination, is that it's plug and play technology. Now, what plug and play means that you don't have to bother about installing the device drivers for any peripherals that you connect. The operating system takes care of it. So every time I connect a new device to my computer, my operating system will detect that something has been connected. It will try to install the device driver. If it's already downloaded, then it will install it from there. Otherwise, it will even search the internet and download a device driver that is appropriate for that connected hardware. Now, once that device driver is made available, then next time whenever you connect that device, the device driver is only loaded into my memory, and I can continue to use that device. So basically, this plug and play technology frees me from the need of carrying device drivers on my own and installing them on my own, because it's a very simple, very standard method of peripherals. Operating system takes care of it itself. So yeah. Now, advantages of devices, especially when you talk about the type A port that's commonly seen right now. It can be only plugged in one direction, but right now we're shifted to type C, which allows for connection in both ways. And it's an industry standard, because of which it is very commonly used, and it can be repaired and replaced very easily. If you have several different types of data transmission rates being supported on USB, type 3.0 supports faster data transmission versus the original type A. And it doesn't mean that if you have a type A port and 3.0 device, it won't work. It will still work. It will support lower data transmission rate, but will still support it. So that means that your devices are backward compatible. Even though if you have an older device and newer USB, USB type peripheral and an older computer, they will still be able to connect. The problem is that cable length is still at right now the max 5 meters, and then data transmission rates is a problem. It's not equal, or it's not the same as parallel data transmission. And finally, right now what we see here is that we're shifted towards it. Where there's a sudden shift towards Type C devices. Now, Type C devices, they just look different. It is USB, but it is Type C. So it means that in the future, the Type A devices may be completely rolled out. So if you have a collection of type A devices, they might not be relevant in the near future. So this is my differences between your internal circuits and universal serial bus.